Okay, the problem we are trying to do here is to take the graph y equals x squared and the graph y equals x, and first see where they cross each other and look at the region where they overlap, and we are going to spin that region or rotate that region first around the y-axis, and secondly about the x-axis. And in doing this, we will form two solids, and our job is to try to calculate the volume of the solid that's generated. Okay, now, the graph y equals x squared is a fairly simple graph. It's a parabola. And the graph y equals x is a straight line. And the region that we're interested in, the region we are trying to rotate is this region in here. And in the first case, we're going to rotate it around the y-axis. So the y-axis acts as like a pencil. And if we take that pencil and we spin that pencil, the region here will rotate around, forming a solid object. And I think the best way to describe that solid object is to consider it as kind of a rounded, like cup. And on the inside, we have bored out a cone. And we remove the cone. So what we have here is a cone cut out of a kind of like a cup shape. All right. Now, as we remember in doing these problems earlier, you want to slice the object, the three-dimensional object, so that you get nice uniform shapes when you slice. I think the choice for slicing here, the best choice, is a perpendicular to the y-axis. So I'm going to slice it this way. And in slicing it, we will then form a circle with a hole in it. Now here's a picture of the object. And as you can see, it's kind of rounded at the bottom and hollowed out inside to where it actually goes down to a point right down here. Now I'm going to slice it this way. And in slicing it, we will form pieces that are circles with holes in them. So what we have is a circle with a hole in it, and we're going to want to take that area and add up those areas from the bottom all the way up to the top. Now you'll notice if I cut down at the bottom, perpendicular to the y-axis, we get a circle with a very small hole in the bottom, almost like just like a pinhole in the bottom, okay? Right down here. All right. So now we're ready to find this area. So that would be pi times big R squared minus pi little r squared. And the big R is the radius from here out to the green curve. So that's going to be the x value on the green curve. So the x value on the green curve for the first circle. The inner circle would be the radius here would be the x value on the blue curve. Now I know it looks like you have 0 here, but not really. because this is the green x, this is the blue x. So we really don't have 0 when we subtract these. We have, well, as you can see, the green x squared is just y. And the blue x squared, since x equals y, will be y squared. Okay? So now we have pi times y minus pi times y squared. And we want to integrate, we want to add up, because that's what the integral does. The integral allows us to add up a whole lot of these little circles. So we're going to start the integral down here and stop the integral when we get up there. So we're going to start at 0 and stop when we get up to here. Now the question is, how far is that? Well, where do these two cross? If you solve these simultaneously, the green and the blue, you will probably notice that this is 1, 1, which means the y values are going to go from 0 to 1, each of the slices forming a circle, and we're going to integrate along the y-axis. Integrate or add up. So this particular expression will go in here. Pi y minus pi y squared. Notice we had to turn the values into y's, the radius values into y's, because the integral was a y integral. Okay, now pi is like a number, so you got pi y, that integrates as pi 1/2 y squared, and pi y squared integrates as pi 1/3 y cubed. We're now ready to plug in the two values, 0 and 1. We plug in the 1 and we get pi over 2 times 1 minus pi over 3 times 1. We plug in 0, and I think you can see that this whole thing over here turns out to be 0, so that'll disappear. And pi over 2 minus pi over 3 is pi over 6. That'll be cubic units. Now I'm going to write that over here by the rotation around the y-axis, because it's going to be interesting, because when we rotate around the x-axis, we're not going to get the same volume. Pi over 6. Now we're ready to take the same region that we used before and rotate it around or about the x-axis. So the x-axis becomes the spinning axis, where that's where you're going to spin. And as you spin, this particular segment will come out here and go down here. The green segment, the green curve, will rotate. And when we're finished, we get a solid object that I'm going to describe in terms of kind of like a cone, where the inside has been cut out in a curved shape, where we start at the top and we kind of curve down until we get to a point down here. A hollowed out cone, but not hollowed uniformly. Okay, so we have this cone shape where the inside has been hollowed out, but it goes down into a point, and it's very thin around the upper edge, gets thicker in the middle, and then very thin down at the end, in fact, to the point where if you pulled off the tip here, you could actually see through it. Now, we're going to take this and we're going to slice it up perpendicular to the x-axis, so the typical slice would look like this. Removing that from the picture, you would get something that looked like that. Now, we want to find the cross-sectional area of that. That will be, again, a circle whose outer radius goes from the x-axis up to the blue curve. The inner radius goes from the x-axis up to the green curve. So now we've got pi big R squared again minus pi little r squared, where big R in this problem is a blue y value. And the little r is a green y value. So what we want to do is we want to add up the smallest one of these way down here at 0 and keep cutting it until we get all the way out here. And again, recall that that was 1 comma 1, so we want to integrate from 0 all the way out to 1. So what's our integral going to look like this time? It's going to look like the integral from 0 to 1 along the x-axis, and here is the cross-sectional areas that I'm adding up. So that's going to be pi blue y squared, but the blue y's equal the x's, so that's going to be pi x squared. And the green y's, y is equal to x squared, so a y squared in green is an x to the 4th. So now we have an integral that looks like pi x squared minus pi x to the 4th. Okay, integrating. This integrates as pi times 1/3 x cubed minus pi 1/5 x to the 5th. Plugging in 0 and 1, we get pi over 3 times 1 minus pi over 5 times 1. And then when you plug in 0 and subtract, the zeros all cancel, leaving us with pi over 3 minus pi over 5. Common denominator there is 15. Common denominator 15. This would be 5/15 minus 3/15 or 2/15. So our two volumes, the one formed rotating around the y-axis, turned out to have a volume of pi over 6, and the volume rotating around the x-axis turned out to be a volume of 2/15 times pi. Obviously they're not equal, and